So last time we discussed the concept of spontaneous symmetry breaking in the Ising model, and we know that in the ordered phase, even though the Hamiltonian is invariant under this Z2 symmetry or the spin flip transformation, but the ground state of the system breaks this kind of spin flip symmetry spontaneously. And today we will introduce another very important concept or idea as a consequence of this SSB, which we call this ergodicity breaking. So we will define what I mean by this ergodicity or ergodic. So we could start from the statistical mechanics that we know very well. And in StatMech, we know that for any observables, we take a statistical average. And what can say about this statistical average is that it is identified with the time average. Suppose we measure any observables many times over time, and we sample around all these different results, and we take a statistical average. And the time average observable should be equivalent to the statistical average or ensemble average. So let me just more rigorously define these two averages. Suppose that the observable, which I call this A, is a function of this eta, where eta is some kind of a dynamical degrees of freedom. It is position or momentum as a function of time. We call this dynamical degrees of freedom, implies that the variables depend on time, so they evolve in time. All these observables are functions of this variables eta, which is a function of time. We could either take the time average by integrating over this observables as function of eta, and eta is function of time, and we take the integral over time and divide it by this t. And when t goes to infinity, this time average is what we call this one way to take the statistical average. But in other way, we could equally well take the ensemble average, and we don't integrate out the time, but instead we integrate over all possible configurations in the variable eta. In other words, we should exhaust all the possible phase space of this eta over time. Suppose the phase space, we call this eta, are momentum or position of these particles and in the many body system, and over time this position and momentum may actually distribute it over the entire phase space. So what this ensemble average means in this definition is to say that we integrate over all possible points in the phase space. So, but this phase space variables varies in time. So all this eta changes a function of time, but suppose we look at the system over a long time, and the system may actually explore all these phase space points entirely. So in other words, system should actually explore all possible position and momentum in the phase space. We should multiply this observable by a probability in equilibrium as a function of that variable. So for each configuration or each points in the phase space, there's a probability associated with that point, which means that if the system appears in that particular point in phase space, there is a probability which we call this PEQ associated with that point, which means that we need to multiply this observable by the appearance, the probability of appearance configuration. And then we should sum over all possible paths, and then this is ensemble average. In statistical mechanics, when we take the time average, and we should think about the ensemble average as well, because the statistical mechanics is justified by identifying the time average with the ensemble average. Okay, so these two averages should be equivalent. In ordinary statistical mechanics, let me define this probability. So this is equilibrium probability distribution of eta. So-called ergodicity refers to the following statement. So in statistical mechanics, we have such a ergodic hypothesis. The word ergodic or ergodicity refers to the description that I just mentioned, that over time we actually explore all possible or exhaust. Okay, so the ergodic hypothesis telling us that as time approaches infinity, this eta I as a function of time comes arbitrarily close to every possible configuration in this eta I phase space. So, which means that in statistical mechanics, we assume that by taking the time average, it is equivalent to take the ensemble average, where we explored all the possible configurations in phase space if time is actually long enough. So that's the reasonable assumption, because we can imagine if we see a point in that phase space, which means that there is a probability for the system to be in that state. We should expect that over a long time, the many particle system should actually travel or explore all these points. So that's our assumption of ergodicity. However, as I mentioned in the very beginning, that in the case of a spontaneous symmetry breaking, say for an Ising magnet, then this ergodic hypothesis is actually breaking. In the presence of the SSB, ergodicity is actually breaking, meaning the system would not explore all possible configurations in the phase space, even if you wait infinite amount of time, which means that the particles never travel to that certain region of the phase space, and they will stuck into certain subspace of this phase space when this ergodicity is breaking. So let me just formally define that. So when the field goes to 0 and the temperature below this transition temperature for the Ising model, the region of the configuration space or phase space with m omega is actually plus m, and m omega is actually minus m are sampled equally. This is when time equals 0 initially. So the observer finds that at this t equals slightly above 0 time, so the net magnetization is actually positive. As we described last time, that for an infinitesimal amount of external field applied to this equally sampled Ising configurations, one of these two states is actually chosen or preferred. So as we argued last time, that when t is actually t1, which is above 0, so when time actually goes down, a large cluster of this m omega, which is minus 1, may form. And the rate to form this large cluster of m minus 1 is about e to the minus beta delta f, where delta f is the free energy of the critical cluster, which is about number of particles to the power of d minus 1 divided by d. So this is just the estimation of the amount of free energy required to form the large cluster of this mb minus 1. So when t is actually moves on to t2, which is even later time than t1, then this magnetization at t2 is actually negative. So just a moment ago, we started to introduce to you the concept of ergodicity breaking in the presence of the spontaneous symmetry breaking. Ergodicity breaking can be a consequence of a spontaneous symmetry breaking. So in the case of the Ising magnet, when the field is 0 and we are below the transition temperature, and we expect that the long-range order will be formed, and the phase space region that with the plus or minus m are equally sampled in the beginning. We don't know whether the magnetization, the non-zero magnetization will be formed when h is exactly 0. So half of the phase space is sampled with m plus and half with m minus 1. But at t equals 0 plus, and if this field is actually turned on just slightly above 0, say plus 0 plus, and one finds that the net magnetization is actually plus 1. So initially at t equals 0, and net is actually 0 when h is exactly 0. But when we turn on the field slightly, and we can find that the net magnetization is actually +1. So we have presented the proof in the previous lectures that the probability in such 0 plus external field for the +1 magnetization is actually a 1, and for the -1 state is actually 0. Okay, so we don't have any probability to find this n-1 state if the external field is actually turned on infinitesimally plus. So let's just argue in the time domain what happens for the ergodicity, right? So when time is turned on at t1, which is above 0, so after initial time, we may expect a large cluster of n-1 to be formed. So we could see that easily from the domain wall argument that we mentioned earlier. But the rate to form such a large cluster of -1 magnetization is proportional to this Boltzmann weight e to the minus beta times delta F, where delta F is the free energy of a critical cluster. And the free energy of a critical cluster is actually proportional to the number of particles to that power, which is d minus 1 divided by d, which is the surface area in some sense. We could just invert this rate to form this large cluster of a -1 magnetization in terms of this e to the plus n times d minus 1 divided by d, which is the time required to form a given state. In this case, this is m-1 state. So which means that the large cluster of a -1 magnetization is formed, but at a rate given by this amount, and we invert that rate is the time required to form such a large cluster -1 magnetization. But you can very easily see that in the thermodynamic limit, so this time is actually what? Infinity, right? So when d is 1, this is actually order 1, but when d is actually larger than 1, say 2 dimensions, so this is actually infinity when n goes to infinity. So which means that it requires infinite amount of time to form a large cluster of -1. And this is the result that is consistent with what we calculated earlier from the Boltzmann weight and probability ratio between these two states. When initially we find the states in the +1 state, it will always stay in that state. And in this time dynamics argument, we see that the amount of time required to form a given large cluster of -1 state is actually infinity. So it takes infinite amount of time to form the large -1 cluster. So which means that the initial condition determines everything. So suppose the initial condition is telling us that the net magnetization is actually in this +1 state, then it always will be in the +1 state. And which means that the ergodic assumption is actually broken. So remember, the ergodic assumption is that when we take the time average of a statistical observable and we assume that this phase space configuration is actually explored everywhere. Okay? So the system explores everywhere in the configuration space. But here we see that it is not possible, because when initially the system is found to be in this +1 state, and it will stay there forever, and you will never have a chance to see this m-1 state. And therefore, the assumption that the system can travel to all possible configurations in space is actually not true. And this is called ergodicity breaking. So when we have spontaneous symmetry breaking, say in the Ising model, and the ergodicity is certainly broken, because initially there's a symmetry link between this m+1 and -1 state, but when we have a spontaneous symmetry breaking and this symmetry is broken spontaneously, as a result, we only have half of the phase space that the system can travel to, and we lose another half because the system never be able to reach that phase space. there's a very closely related link between the ergodicity breaking and the spontaneous symmetry breaking. So when we have the ergodicity breaking, it must imply that we have a spontaneous symmetry breaking. But the reverse argument is not always true, so we should come back to this later. So I guess that completes the argument and introduction to the very important two concepts. One is the spontaneous symmetry breaking, another is ergodicity breaking. And both concepts are really crucial important in order to understand phase transition and statistical mechanics. So now let's go to another very important part of the argument, as I mentioned earlier, which means that we should link the fluid to the Ising model or lattice gas. Remember, previously we mentioned that the universality clause exists in many systems of many body systems, and in particular we say that the Ising model is in the same universality clause as the liquid gas transition. But we didn't give you a proof, but now it's time to prove that near the transition, these two systems seemingly different, but they have exactly the same critical property at the transition. But it requires some mathematical derivations. So now let's go from the fluid part, and we should consider there are many molecules or particles living inside of a box, but they interact with each other by some kind of interaction, which I call this Uij, and suppose there are n particles. And those particles are continuously distributed in a box, so that we call this system a fluid, because they they can float, and there's no lattice. And so we consider a fluid of n particles inside the box at this position vector Ri and momentum Pi. And they are interacting with each other by this kind of interaction, Uij, where Uij may be a long range or short range interaction. Okay, so we will specify this Uij in just a moment. So the Hamiltonian of such a fluid is given by the following, so summation over all particle states of a kinetic energy, P squared over 2m, and potential energy of a single particle, plus the two-body interaction, where the two particles at positions Ri and Rj are coupled by this U2, two-body interaction. And we could generalize this to, or consider a three-body interaction, and so on and so forth. So then we could try to calculate this partition function of such a fluid of n particles inside the box, and then we try to link this partition function to so-called the lattice gas system, where you consider the system as many small cubes, and inside that small cube there are just two possibilities, that either you find a particle inside the cube or you don't. Okay, and these particles actually can be considered as hardcore particles, and you cannot cross the particle each other. So later we will compute the partition function of this fluid, and we should map this partition function of a fluid to the system of a lattice gas. So let's take a short break. So let's continue. As I mentioned just a moment ago, that we now are in the position to derive the universality clause between the Ising model and the liquid gas transition. And the way that we prove that equivalence at the transition between these two systems is by computing the partition function for n particle fluid in the box, and then we try to map the system onto a so-called lattice gas system, and then from the lattice gas we further map it to spin system. Okay, so this is the path that we should go. And so first let us just write down the Hamiltonian and partition function for an n-particle fluid inside the box, and they are interacting by Uij function, and also there's an on-site potential for every particle inside the box. So the Hamiltonian of this system is written here, where we sum over the kinetic energy for a single particle and the on-site potential energy, and also a two-body interaction and three-body interaction, and so on and so forth. And the grand partition function C is defined by tracing over such a e to the minus beta h minus mu n, where mu is the chemical potential of the system. And the trace for this system is defined by sum over the particle number from 0 to infinity, and inside that summation we have a product of that, a small volume factor of this phase space configuration, and the phase space consists of the momentum and the position vector, and this small volume of a configuration space should be divided by this Planck constant, okay, h, to make this partition function applicable for quantum mechanics. So we could take advantage of this Gaussian integral of that type, where this integration over the p, the moment integration over the kinetic energy term, e to the minus beta p squared over 2m, is just a constant, independent of momentum, but depends on the temperature, inverse square root, dependent on temperature. And this factor is called the thermal wavelength. And we will use that thermal wavelength later. So then we try to combine everything by taking advantage of such a definition and the Gaussian integral, and we plug in those vectors into the grand partition function. So now the C is given by this. So this is minus beta mu of n 1 over n factorial qn. So notice that mention here over this particle number n, in this case, implies that we don't fix the particle number, total particle number, but we could just consider all possible total number of particle n from 0 to infinity. So we consider all possible system where the total particle number is at 0 or 1 or 2 and up to infinity. So we consider all possible situations where you have a different total particle number. And we could just rewrite this partition function in that simplified form, where Qn is given by this e to the minus beta sum of I u1 Ri plus j2 Ri j plus sum of I j k u3 Ri j and Rk. All right, so we can rewrite this partition function in that form and pull out all these prefactors after this Gaussian integral, and we can define the so-called grand free energy. Capital F is called free energy of a grand canonical ensemble, or grand free energy. And this capital F is a function of temperature T and chemical potential mu. So we could just define such a grand free energy by taking the log of this partition function C. So at a finite size, the grand free energy, capital F, is a function of the temperature and chemical potential. Of course, it is also a function of this U, the potential. All right, so this follows from the standard statistical mechanics that we take minus kBT log of this partition function, we get this grand free energy. And this U2 and U3, consider this potential has a hard core, meaning the total number of particles is actually smaller than or equal to so-called the maximum number of particles that can be packed into such a finite volume. So this NCP is the maximum number of particles that can be packed into a finite box, which means that inside a small box, we could have at most that number of particles, NCP, inside this box. And we consider that as our a reasonable assumption. So let's just continue defining this free energy density, little f b, which is the capital F divided by the volume. And this is the one way to define the pressure of the system of fluid. And we know from standard statistical mechanics, we have such a relation between the free energy density and entropy and the number density. So rho is the number density. So then we should calculate this free energy, the ground free energy, as a function of the temperature, mu, and this potential U, and under such a hardcore condition. But we know that from the statistical mechanics that the pressure, which is related to this number density, has that kind of analytical properties that we introduced earlier, and this free energy density of the bulk actually shows a convexity up property. As a result, you can find that this pressure, this function of mu and T, is actually positive, definite, or zero, and it is continuous. And dp d mu, which is the number density, is actually positive, definite as well. And the first derivative is the pressure is back to the temperature, and with the chemical potential exists almost everywhere. And the entropy, which is the partial P partial T, where T is temperature, is always positive, definite. And this function is a monotonic, non-decreasing, because it is related to the specific heat that we introduced earlier. And finally, the dp d mu is actually positive, definite, and also it is a monotonically non-decreasing function, which leads to the positive, definite of thermal conductivity or thermal susceptibility, kappa T. So all these nice analytical properties of this free energy density of the bulk follow precisely of these properties that we introduced earlier, and those properties should hold in the fluid situation here. So let's take a short break. When we come back, we will try to map this grand partition function and free energy of the fluid onto the system of a lattice gas. Just a moment ago, we tried to compute this partition function of a fluid, and inside the fluid, we have m particles, and they interact by this potential, the on-site potential, and two-body interaction, and three-body interaction, and so on. And they have this translational symmetry, and which, for example, makes this two-body interaction, U2, a function of the distance between these two sides on I and J. And we impose particularly there's a hardcore condition which says that in reality the total number of particles is actually a fixed finite value, which we call this NCP, which is the maximum number of particles that can be packed into this cube or the box. As a result, this partition function, when you sum over this whole possible total number of particles, has an upper bound or upper limit, NCP, which is not infinity. As a result, your partition function, after summing over all possible total number of particles, is still a finite value, and that leads to the finite value of the free energy. Or the free energy is not a singular function. As a result, you get all the nice analytical properties of this free energy density, follows all these analytical properties. So now let's try to map this fluid system onto a system we call this lattice gas. So in the fluid, all these particles can move freely. They are not constrained in a tiny little cell inside a box with a hardcore condition. So the fluid can actually flow freely, and there's no unit cell inside that box, except that we fix the total number of particles inside the box as a finite value. Apart from that, there's no lattice structures of the box. So that's what we call this fluid. It's a continuous distributed many particle system. But now we would like to map this continuous system onto the system with the unit cell and with this lattice structure. So in that lattice gas limit, we consider a small unit cell or a small box inside this big box. And so the big box consists of many small boxes. right? So there are many small unit cells, and we give the system a kind of structure, a lattice structure or hardcore condition, that the particle could be either occupied in a single box or there's nothing in a single box, small box. In other words, the distribution of this kind of particle now could be equally well described by this particles living inside a smaller cell. You could have either one particle inside a small cell or 0 particles. And this big box consists of periodic array of these smaller boxes or smaller cells, and where in each cell we can allocate a single particle or no particle there. Okay? You cannot have 2 particles in the same smaller unit cell because we have a hardcore conditions on this smaller cell, meaning the particles cannot collapse or overlap with another particle inside that smaller unit cell. But in fluid, there's no such a restriction or structure like this, but we try to link this two. And the way that we link this two is to think about this density, microscopic density of a fluid as a function of the position, and we could try to relate microscopic density to such a hardcore unit cell by defining the microscopic density as a function of sum over delta function. You know very well what this delta function looks like. So this is your delta function, and this is position, and at position Ri, you get delta function, which goes to infinity when R hits Ri, but 0 otherwise. So it is a very sharp peak which describes a single particle location. In other words, single particle could be located exactly at that particular position Ri, and we assume that there is some lattice constant involving in this big box, so that there are many smaller boxes, and all these particles could live a state in one of the smaller boxes. And the distribution of this microscopic density is a delta function like. So you could consider this kind of a delta peak right here when the position hits Ri. And the total number of particles is just the sum of all this delta function, or integrated over the real space of this microscopic density function consisted of the bunch of delta function. But the advantage of using this delta function to rewrite this microscopic density and rewrite this partition function is the following. We look at this two-body interaction, U2, in the fluid language, but we could rewrite this two-body interaction between nearest neighbor sites in terms of this microscopic density, which is the delta function, right? So U R minus R prime delta R minus R1 and delta R minus R prime. You sum over, integrate over R and R prime, and you consider the interactions between this any two particles is actually expressed in terms of this product of this delta function inside this integration. Okay, so but we could rewrite this in terms of the density rho in the following manner: rho of R, rho of R prime. Okay, so you could simply just plug in the definition of this density function rho here, and you get back to this. And if you use this definition of the density rho, and you plug in here, there's a sum over this bunch of delta function, and you immediately recover this expression here. And if you use this mathematical identity, f of x delta x minus y, and dx f of y, sum over x or integrate over x from minus infinity to plus infinity, you get to the f of y function after performing such integration over the x of this product of the two functions between f and delta function. Okay, so you could easily show that when you use this nice properties of delta function, and this recovers this fluid two-body interaction form, which is sum over nearest neighbor U2 interaction term. Okay, So in other words, these three formulas are equivalent under the definition of this microscopic density, rho of R, but we can play more tricks to the density-density interaction form of this two-body interaction. So you can see very clearly that these two particles at different sites, I and J, interact with each other by the density. So this is R and R prime. So there are two particles, R and R prime, and they interact by U2. But the way that we think about this U2 interaction in terms of the particle density is that these U2 actually mediate interaction between these two density of particles at R and R prime. And you can consider such kind of interaction as a density-density interaction. So this immediately tells you that U2 should be interpreted as the density-density interaction, which is the case when we consider the Coulomb interaction, right? So the Coulomb interaction is nothing but density interaction of the charged particles, okay? So here it's just a neutral particle density interactions, and we could just cast this U2 density interaction form. But this plays a crucial role when we try to map this lattice gas system onto this Ising model. So after we change our variables from this position and momentum variables in a continuous fashion to this density distributions, and we are able to map further this expression of a partition function onto this Ising model. So let me just write down once more the Hamiltonian of a kinetic energy, the potential energy term. So using that density variables, rho, we are able to rewrite this potential energy terms of the Hamiltonian of a fluid in terms of, the particle inside a unit cell, and as I mentioned, we could define this particle in the box to consist of many smaller boxes, and either there's just a single particle inside a smaller unit cell or nothing. So you could have the so-called occupation number of particles inside a small unit cell. So this Ni could take only two possible values, either 0 or 1, and when it is 1, we said this site is occupied. When it is 0, it is an empty state. And that kind of a hardcore smaller unit cell description of this fluid is actually consistent with what we defined earlier, this microscopic density as a bunch of delta function sum over. So we can use such a delta function kind of a distribution of a particle to further actually map the system into this kind of 0, 1 smaller unit cell with either single particle or no particle in there. And such new variables inside a smaller unit cell, or this occupation for each lattice point, so I and J are lattice point or lattice site. Under such a language, we already transform our partition function or Hamiltonian from the fluid system to the lattice gas. But then we could further transform the language of variables from this lattice gas to the Ising model. So this is the lattice gas version. So the way that we map this occupation onto the spins is by the following identifications between the spin of an Ising model and the occupation on each of the unit cell. So this further map this lattice gas onto this Ising model. So time is up for today, and we haven't finished this derivation or mapping from the fluid to the Ising model, but we will. It's just the final step after this kind of identification between the occupation variables and the spins. And we will continue in the next lecture. See you next time.